other conductor, and C is the capacitance, which is what I say is a purely geometrical quantity, and delta V is the potential difference between those two conductors. So this is the master equation, okay, that we're going to be using today. And then, let's go to the circuit stuff over here. Okay, so something about symbols. If you see two lines like this that are parallel and then like that, that represents a capacitor. The two lines of equal length mean they represent like two sheets, conducting sheets that are parallel to one another, going into and out of the board. In your case, into and out of your paper. And then this is a wire here, and this is another wire. Right? And so these are the two conducting plates. So that this is the same as a capacitor. If you draw the symbol with one long line and a short one, again, this is wires. That's a wire, and this is another wire here. Then this represents a DC battery. The longer bar over here represents the terminal of the battery that is at the higher electric potential. And the shorter one represents the terminal of the battery that is at the lower potential. So in this picture here, right, that's a battery. It's two lines that are parallel but not of the same length. If the two lines are parallel and they have the same length, it represents a capacitor. But if the two lines are parallel and one is shorter than the other one, it doesn't represent a capacitor, it represents a battery. And then a switch is like, you have a wire. That can then, be disconnected from another wire. And you can throw this to the on position, or you can throw it to the off position, right? So this just represents a switch. To turn on, turn off. Yes?
I'm not sure if this matters, but will the long side always be the positive side and the short side always be the negative?
Yeah.
Okay.
It's longer to represent the terminal that's at the higher potential.
Okay.
And that will be the positive terminal of the battery. And then the shorter one, it's shorter because it is the terminal of the battery that is at the lower potential. Always.
Okay.
So in this picture over here, notice how the shorter one to the left, that's the negative terminal of the battery, and the longer one to the right is the positive terminal of the battery.
Yes.
Okay? Now, when are capacitors said to be connected in series? When are they connected in parallel? So, what's important to note when they are connected in series is that, see, this here, these two parallel plates represents one capacitor, and these two parallel plates represents another capacitor. If you connect one of the conductors, one plate of this capacitor to the other plate, or to one plate of the other capacitor by just a wire like that, with nothing in between, like no other wires connected, then these two are said to be in series. So the analogy that I like is, you can think of capacitors as people with one conductor and another conductor, as long as they have both arms or both hands, God willing. And if you shake hands with someone, it's one of your conductors with one of the conductors for the other person, and then I could be, touching something else, and then we are connected in series. Right? So this line over here would be like, it's like this capacitor is shaking this hand with this capacitor. They're shaking hands. There's a connection. There's one line, one connection from one conductor to the other with no junctions in between. There's no other wire connected over there that goes off to some other place. So if I shake hands with Min, for example, and we shake hands and then you touch us, then see, if I shake hands with her and it's just the two of us, then we're connected in series. But as soon as you touch our hands, then we're not in series anymore. And you'll see this will make more sense when we talk about resistors, because in the case of resistors, we're going to be talking about the current through one circuit element and the current through the other circuit element. And if whatever current, I have, if the flow of charges is just has one path to the other one, it will be the same current in the other one. So we'll be connected in series because we have the same current. In this case, what happens when capacitors are connected in series is that they have the same charge. So if the charge of this is 20 coulombs and on this, well, this one has to also be 20 coulombs. And by 20 coulombs, I mean plus 20 in one conductor, minus 20 in the other conductor, and then plus 20 and minus 20 coulombs in the other conductor. So let me get rid of these symbols here. So I am going to write like a table over here, or a set of formulas. So what do we need to know if we have capacitors connected in series? So the issue is this. So we have a voltage source over here, like a DC battery. Let's say like this looks like a car battery to me, but it could be a AA battery, a AAA battery, just a battery with a positive and a negative terminal. Suppose I take a wire and I connect it to the positive terminal of this battery, and that wire bends and connects to that conductor, to that conducting plate of that capacitor. Then there's a gap right in between. There's an insulating material between this conductor and this conductor, and then you use another wire to connect this plate to this plate of the other capacitor, and then there's insulating material in between these two, and then you use another wire to connect it to the negative terminal of the battery. So these two capacitors are said to be connected in series. The circuit representation of this connection here is shown over here. So delta V is the voltage across the terminals of the battery. And then when these capacitors get charged, this capacitor is going to have a charge Q1, and this capacitor is going to have a charge Q2. And the voltage across this capacitor is delta V1, and the voltage across this capacitor is delta V2. The capacitance of this is C1, the capacitance of this is C2. So the capacitance do not have to be the same, because remember, they depend on the geometry, like on how big the area of the plates are, how far away the plates are from one another. So these capacitances are usually not the same. And the voltage across this, and it's delta V1, the voltage across this is delta V2. So the question becomes this, and the charge on this is Q1, and the charge on that is Q2. The question becomes, if I were to replace these two capacitors by a single capacitor that is equivalent, in other words, this capacitor by itself will be equivalent to these two together connected in series like this, what will be the voltage across this capacitor? What will be the capacitance of it? And what will be the charge of it? So that this simple circuit with just one capacitor is equivalent to this circuit. So when they are connected in series, what happens is that the charge of this capacitor happens to be the same as the charge of that one. So the charge on this capacitor that is equivalent to these two capacitors connected in series is that the charge of this is equal to those two charges. So we have this formula, that Q equivalent, that means is the charge in the capacitor that is equivalent to those that are connected in series is equal to Q1. That's equal to the charge in one of the capacitors, and it is also equal to Q2. And if you have more capacitors connected in series, then you'll have Q3, and so on. So when capacitors are connected in series, they all have the same charge. Now, what about the voltages? What is the voltage across the capacitor that's equivalent to the other capacitors connected in series? So what will be the voltage across this? Well, the voltage across this will be equal to the sum of the voltages across the individual capacitors connected in series. So delta V1 plus delta V2 plus, if you have more capacitors connected in series, all the voltages add, and they add up to the voltage across the capacitor that is equivalent to them. And what about the capacitance? C. So the capacitance of the capacitor that is equivalent to the ones connected in series are related to C1 and C2 by this formula. And if you have more of them, you'll have that. So these are the three equations that we need to apply when we recognize capacitors as being connected in series.
What does EQ mean?
Huh?
What does EQ mean? Like Q, EQ, VQ. I understand it's like the
This
total.
is the voltage
Yeah.
across the capacitor that is equivalent.
Oh,
EQ
equivalent.
is equivalent.
Okay, thank you.
So this is the capacitance of that capacitor that is equivalent to the.
To the sum.
So this capacitor by itself is equivalent to these two capacitors.
Right. Okay.
So what is the voltage across that? What is the capacitance of that if the capacitance of this one is C1 and C2? And what is the charge on that one? If the, how does the charge across on this capacitor compare to the charges in the capacitors that are connected in series? Yes? So I have those formulas here in my notes. That's what I just wrote down on the board. Now, what happens when capacitors are connected in parallel? So imagine that the connection is such that this is a DC battery, and I take a wire and I connect it to the negative terminal of the battery, another wire connected to this positive terminal of the battery, and I grab those wires and I just connect them to the two conductors of this capacitor C2 here. But then I form a junction here and there, and I connect with other wires to the two conductors of another capacitor. So now those two capacitors are said to be connected in parallel. And that would be if, for example, we were to hold both hands. Then you and I would be connected in parallel. And again, how do you represent this using symbols for circuits? Well, this battery is represented by that symbol. This capacitor is represented by two lines that are of the same length. This capacitor by that one. Let's call this one C1, this one C2. The charge on this one Q1, the charge on that one Q2. So if I replace these two capacitors by one single capacitor, that will be equivalent to these two capacitors connected in parallel. How would the parameters that describe this capacitor here, that's equivalent to them, how does it depend on the parameters of these individual capacitances or capacitors? So we have another set of formulas for capacitors connected in, how about I say, in series. Number 2, capacitors connected in parallel. Now, what happens here is that Q equivalent, that means the charge in the capacitor that's equivalent to the other ones is not equal to Q1 and Q2, but it's equal to the sum. So this will be Q1 plus Q2 plus, if you have more capacitors connected in parallel, the sum of all of their charges adds up to the charge of the capacitor that's equivalent to them. The voltages turn out to be the same. And you'll see why that's the case later on. It's the same for all of them. And the capacitances add. And that's what I have in my notes over there. That has to do with charging capacitors. Let me solve an example. I'm going to go through this example in great detail. So, the circuit that I want to solve is, let's see, it looks like maybe here will be better. So, so let's give them some numbers, and then capacitors connected in parallel. I'm just rewriting those equations that I have over there because I want to use that board. Okay. Oh, and then I forgot the master equation. The master equation here means that if I know any two of those three quantities, I can figure out the third one. So if I know the charge and the capacitance, I can tell you what the voltage is. If I know the voltage and the capacitance, I can tell you what the charge is. And if I know the charge and the voltage, I can tell you what the capacitance is, right? If I know any two, I'll know the missing quantity. So, the example that I want to solve, which I didn't type yet, or I have it typed but not posted. So what if we have this following circuit? This is point A. And we have a 4 microfarad capacitor here. And this is a 2 microfarad capacitor. I suggest you draw this big. Really big. Like, use the whole page. And then the next thing that I'm going to draw it on another page. Because what I'm going to do is, I'm going to go this way, and then I'm going to have to go backwards. And so we'll be filling in stuff, and you'll need space too. So I just suggest you, well, this is what I did in mine. I guess you can put it all maybe in one page, or just a couple of pages you can do that. So this will be this is also 2 microfarads. And I'm going to put a problem similar to this in the exam. The next one. So this one is 8 microfarads. I mean, some circuit. This is 4 microfarads. But you'll have to use the same approach. And in the example, we are given that the potential difference between points A and B, let's define that as delta V, AB, is 60 volts. So, point A and point B differ in potential. The voltage between those points is 60 volts. Now, which one is at the higher potential, A or B? How do you know? Right, I wrote VA minus VB. So if I take this difference and I get a positive number, that can only be true if the potential at A is bigger than the potential at B. Yes? So, what that means is the following. Suppose the potential here, don't write this down, don't write this down. Suppose the potential here is 100 volts. Therefore, what's the potential here?
40 volts.
Exactly, 40 volts. So that the difference is 60 volts. Suppose the potential here is 200 volts. What will be the potential here? 140. So that the difference is 100 volts. It's 60 volts. Suppose the potential here is 60 volts. What will be the potential here? 0, because the difference is 60, right? So that is all that means. It just means the difference in potentials at those points in the circuit, is 60 volts. And since I wrote it in this order, VA minus VB, this is common notation. Delta V, and then you see as a subscript AB, it means the potential at A minus the potential at B, right? And so anyway, that's what that means. Now, what we want to do is, we want to calculate, I want to know what the charge, so I connect A to B to this 60 volt voltage, and I let things, let the circuit do its thing, and then the capacitors will become charged, and then I want to know when everything is fully charged, what is the charge in this capacitor, what's the charge in this one, what's the charge in this one, charge, charge, charge. And also, what is this voltage, what is this voltage, what is this voltage, what is this voltage, what is that voltage, what is that voltage. So, that's given, right? So, question. Calculate the charge and the voltage across each capacitor. What is the voltage? What is the charge? What is the voltage across each capacitor, and what is the charge in each capacitor? So, what I am going to do is, here's how I am going to solve this problem. I am going to simplify the circuit. I'm going to simplify it. And hopefully at the end, I'll just have one capacitor that's equivalent to all of them. So, what do you notice? Do you notice any specific connections between capacitors? This is connected to that in blue, and this one with that in blue. Yeah?
The ones in parallel are when they're
Which are in parallel?
the ones that when it breaks off into two,
So,
two extras already off the two extras. So 2 and 2, and then 4 and 4.
So these guys are connected in parallel. Agree?
And they're also the same capacitance. Each capacitor of the ones in parallel are of the same capacitance.
Yeah, two are the same?
Yeah.
But that was only because I was given. I could have said this is 6, or this is 10, or this is 27. I could have given that. It's just that in this example, so that I chose this problem so that we don't need a calculator.
Oh.
So what I'm going to do is, agree, he's correct. these two capacitors are connected in parallel, and these two capacitors are connected in parallel. So what I'm going to do is I'm going to redraw the circuit, and I'm going to include this, but then this will be replaced by the capacitor that is equivalent to them. And these two are going to be replaced by the capacitor that's equivalent to them. So let me redraw the circuit again. So this is A, terminal A, so it goes like this, right? And then we have, that's the 4 microfarad capacitor. I'm going to leave that by itself. And now, this 2 I will replace by 1 capacitor. I don't know what it is yet. Now this 2 I will replace by 1. And then this one is by itself. I'm just going to draw that again. And that's B. So I know that this one is 8 microfarads. The question is, what's this? And what's this? So let me do this one at the top first. How are these two capacitors connected? In series or in parallel?
Parallel.
In parallel. So how do I combine them? When they are connected in parallel, I look at equation number 6. So what do? I just add them up. So the capacitance of this guy is going to be how much? 2 and 2 gives me 4. And how are these two capacitors connected, the 4 and the 4? In parallel or in series? In parallel. So they will combine to a capacitor that's equivalent to them with capacitance of 8. Yes or yes? Now I want to see if I can further simplify this circuit. So this is A. So what do you notice? Is there something you notice?
Now it looks like a big parallel with 2 in series.
So which 2 are in series?
The 4 and the 4 on top capacitors, and then the 8 and the 8 on the bottom.
Agree? So these 2 at the top are connected in series. I'm going to replace them by 1 capacitor. And these 2 at the bottom, I'll replace them with 1 capacitor, and realizing that they are also connected in series. Now, when capacitors are connected in series, how do their capacitances combine? Capacitors in series, so I got to look at equation number 3. So I got to use this equation, right? So for the 4 and the 4, I'm going to do 1 over C equivalent equals 1 over 4 plus 1 over 4. And a quarter plus a quarter is a half. Now remember this step. The capacitance therefore is 2, right? Because you got to take the reciprocal of that. So the capacitance of this is 2 microfarads. Yes or no?
Why is the equation the reciprocal? I'm just curious.
I gave you the equation. Bless you, I haven't told you why. I mean, essentially it's like this. If I take this here, right, delta V, let me just do it for a couple of them. Oh, why not? 3 of them. It's that, right? Now, if I use this formula, the voltage across each one is the charge divided by its capacitance, right? So it will be Q equivalent over C equivalent equals Q1 over C1 plus Q2 over C2 plus Q3 over C3, right? But by this formula number 1, Q equivalent is the same as Q1, as Q2, as Q3. So this cancels that, cancels that, cancels that, and I get which is that formula. So just comes out like that. All right, what about the 8 and the 8? So I'm going to say 1 over C prime equals 1/8 plus 1/8. That looks like 2/8 to me, which is what? 1/4. And then C prime is going to be 4, right? Yes? Yes. And then finally, one more step. How is the 2 microfarad capacitor connected to the 4 microfarad capacitor? How is this? Capacitor connected to this capacitor. In parallel. And when they are connected in parallel, what do? I just add them up, right? So therefore it's going to be, this is point A, actually, and that's point B. And now I'm down to one capacitor that's equivalent to all of them. And if they are connected in parallel, 2 plus 4, right? In parallel, I just add them up. 2 plus 4 is 6. 6 microfarads. Agree? So all of these capacitors connected in this manner in this circuit can be replaced by this one single capacitor that's equivalent to them. It's sort of like, if you like, you can think of those as a whole bunch of vectors, and this is like the resultant of them. You know, the resultant vector by itself is equivalent to all the vectors added together, right? Individually. So, but what did we say is this potential difference over here? 60 volts, right? That was given, right? That's this. And remember, from my master equation, if I know any 2 quantities, I can figure out the third one, the one that I'm missing. What am I missing over here? The charge. And that will be by the master equation, it's C equivalent times delta V equivalent. So that would be 6 times 60, right? So this is 6 microfarads times 60 volts. That's going to be 360 microcoulombs. Yes? Which of those 2 points did we say is at the higher potential? A or B? A. So this is the positively charged plate, and that's the negatively charged plate. Writing that the charge in the equivalent capacitor is 360 is saying that the charge on this plate here is plus 360 microcoulombs, and the charge on the negative plate over here is minus 360 microcoulombs. And when you say this, that's what it means. Plus Q in one conductor, minus Q in the other conductor. But you just said that the charge in this capacitor is 360 microcoulombs. Notice that even though we were given microfarads over here, and micro is micro, right? It's 10 to the minus 6, right? But I never had to use that. I never used 10 to the minus 6. The voltage was given in volts, so that was in volts. So farads times volts is coulombs, and then I just write microcoulombs. Right? Now, I haven't answered the question. The question is, or the question was, what is the voltage across and the charge in each capacitor, right? What I just found was the voltage that was actually given. I found the charge and the capacitance of the capacitor that's equivalent to all of them. Now what I need to do is work backwards. So here's the way that I do it. And remember that I said last time that the nice thing about these problems is that we can check if we're doing the problem correctly. So we're going to be doing that as well. So now I'm going to go backwards, and I ask myself this question. In my last step, I went from this circuit with two capacitors to this one, right? How did we say these two capacitors were connected to be replaced by this one? They are connected in parallel. What's the same for both of those capacitors connected in parallel? That's also the same as this one that I have already solved. What's the same for all of them if they're connected in parallel? The voltage, right? If they're connected in parallel, they'll have the same voltage. And since the voltage across this is 60 volts, then the voltage across this is 60 volts. And the voltage across this is 60 volts. But wait a minute. If I know any two quantities, I can figure out the third one, right? What am I missing? Now I'm missing the charges, right? And how do I calculate the charge in each capacitor if I know the voltage across it and the capacitance of it? I go to my master equation and I figure out the charge by doing what with the capacitance and the voltage? I multiply them. Right? So 2 times 60 is 120 microcoulombs, and 4 times 60 is 240 microcoulombs. Agree? Now let me check. Let me check to see if I did this correctly. We said we just calculated the charges, right? And they're connected in parallel. How are those charges that I just calculated, how do they relate to one another and to this one, to the charge of the capacitor that's equivalent to them, when they are connected in parallel? Well, the two charges have to add up to the charge of the capacitor that is equivalent to them. So is 120 plus 240 the same as 360? Yes, so we're good. I just checked and we're good. I didn't make a mistake. Yes? I'm going to keep doing the same thing. Now I'm going to go back. I'm going to say, this capacitor came from where? This came from which combination? These two connected, how did we say? In series. So now that you recognize that they're connected in series, what do these two capacitors have that's the same as this one? Well, I look at my formulas here, they're connected in series. What do they have that's the same for all of them? The same charge, right? But I know everything about this capacitor. I know that the charge is 120 microcoulombs, right? So then the charge in this one is 120 microcoulombs, and the charge in this one is 120 microcoulombs. Right? This is C, and this is C. But wait a minute. If I know two quantities, I should be able to figure out the third one, right? What am I missing? Potential difference, right? And what am I missing? Potential difference, right? So how do I find the potential difference across the conductors of a capacitor if I know the charge and the capacitance? I go to my master equation, and what do? I take the charge and I divide by the capacitance, right? So how much is 120 microcoulombs divided by 4 microcoulombs? Notice that the micro will cancel. So what do I get? 30 volts. And how much is 120 microcoulombs divided by 4 microfarads? Okay, I just found those two voltages. Did I make a mistake? Maybe I multiplied them when I was supposed to divide them like I just did, right? Now let's check. These two capacitors are connected, we said, in series. How do their voltages, which I just calculated, relate to the voltage of this one when they're connected in series? Well, when they're connected in series, the voltages have to add up. So is 30 plus 30 the same as 60? Yes. So good. Questions? I'm going to keep doing the same thing. I'm going to ask, how did I combine these two capacitors and replace them by this one? I said that these two capacitors, the 8 and the 8, are connected in series. So there's something that they have that's the same for both of them as this one. What do they all have that's the same when they're connected in series? The same charge. So since the charge in this one is 240 microcoulombs, then the charge in this one is 240 microcoulombs. Maybe now you're realizing that I was right when I said draw big, right? Or because you run out of room, most likely. But wait a minute. If I know any two quantities, I can use the master equation to figure out what I'm missing. What am I missing over here? The voltage, right? I got the capacitance and the charge, so I'm missing the voltage, right? And how do I find the voltage? How do I calculate the voltage if I know the charge and the capacitance? I just divide them, right? So how much is 240 microcoulombs divided by 8 microcoulombs? The micros cancel. What do I get? 30 volts, right? And the same for this one, right? Well, did I make a mistake? I just found their voltages, right? When they're connected in series, like we said, how do their voltages relate to one another? They have to add up, because they're in series, they have to add up to the voltage of the capacitor that's equivalent to them. So it's 30 plus 30, the same as 60. Yes. I'll just call them all C, but you know, they're not, obviously they're not the same. Now, this capacitor here is this one, right? So I have solved this one already. The charge here is 120 microcoulombs, right? And the voltage across it is 30 volts. This capacitor here is the same as this one. So I have solved that one too. 240 microcoulombs. And the voltage is also 30 volts. Now I gotta do this two, and I gotta do this other two. Questions? No questions. So what am I gonna do? The same general approach. I ask, okay, these two over here came from or combined to give me this one, right? So how did we say these two capacitors combined to give me this one? We said that those two are connected in parallel. So what do they have that's the same for both of them and for this one, which I have completely solved already? They all have the same voltage, the same potential difference, which is the voltage. So since the voltage across this is 30 volts, then the voltage over here is 30 volts. And the voltage across here is 30 volts. But wait a minute. If I know two quantities, I can figure out the missing quantity. What am I missing? It looks to me like we're missing the charge, right? And how do I get the charge? If I know the capacitance and the voltage, I multiply them together, right? So, how much is 2 times 30? That's 60 microcoulombs. And what about this one? 30 times 2 is also 60 microcoulombs, right? Did I do that right? Did I mess up? Did I make a mistake? Well, we can check. I just found their charges, right? How did we say these two capacitors are connected to be replaced by this one? We said that they are connected in parallel. So how do their charges relate to the charge of the capacitor that is equivalent to them when they are connected in parallel? Oops, parallel is here, so they have to add up, right? To the charge of the capacitor that's equivalent to them. So is 60 plus 60 the same as 120? And we're good. And now the last step is, what are the charges of these capacitors and what are the voltages across them? Well, what did we say? And these two combined in to give me this one. What did we say? How did these two capacitors combine to give me this one? In parallel. And what do they all have the same when they're connected in parallel? Voltage. And what is the voltage across this guy here? 30 volts. So the voltage across this has to be 30 volts. And the voltage here has to be 30 volts. So, what am I missing? The charge, right? So the charge here would be, and the charge here would be what? Well, how do I get the charge? If I know two of the quantities, I multiply the capacitance by the voltage. So 4 times 3 is 120 microcoulombs, and 4 times 3 is also 120 microcoulombs. And I'm done. Oh, wait a minute, I gotta check. Did I do that right? Did I mess up? I just found their charges, right? So, and they're connected in parallel. How do those charges, when they're connected in parallel, how do those individual charges relate to the charge of the capacitor that is equivalent to them? Well, they add up according to that formula. So is 120 plus 120 the same as 240? And I'm good. I'm completely certain that I did that problem correctly. The nice thing about it is that I never needed a calculator. It's convenient. Because problems with capacitors can drive you nuts with the calculator. Now, why? Let me discuss this. Let's see, green. I'm going to use green. Suppose the potential here is how old are you?
20.
20. It's 20 volts. That's the potential there. If you don't go across anything in the wire, the potential stays the same. So the potential here is 20 volts. 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 The potential, let me keep over here. Potential here is 20 volts. The potential here on this plate is 20 volts. Okay? And remember, this was the higher and this was the lower potential. Now, the question is, what does this mean? When you say that the potential difference across those two plates is 30 volts, that means that the potential here has to be what? And that's the negative, right? So that's the low one, so this one has to be the higher one. What should be the potential there? 50 volts, because the difference is 30 volts. And you're going to higher potential, right? So the potential here is 50 volts, here is 50 volts, here is 50 volts, here is 50 volts, right? Because I haven't gone across anything. But wait a minute, this was 20, so this was 20 volts, so this is 20 volts over here. So what is the potential difference between those two plates? Now, why do we say that this capacitor is in parallel with that? Because if you're walking and you're here, when you get to this point, it's a junction. You can either go this way or you can go this way. And either path you take, the potential difference is going to be the same. Because the potential here is 50 volts. And when you get over there, it'll be 20 volts. So the difference is 30 volts no matter whether you go this way or that way. That makes them in parallel. And if we continue, this would be 50 volts. This would be 50 volts. Now, what does it mean when you say that the potential here is 30 volts? That means that, what will be the potential here? 80 volts. They differ by 30 volts. So that's 80 volts, 80 volts, 80 volts, 80 volts. Notice, what's the potential difference between A and B? That's 60 volts, right? We're good. And if I continue on this side, this is 80 volts, this is 80 volts. It only changes if I go across something. So when I get over here, this will be 80 volts. And this will be 80 volts. Now, over here, the potential was 20. This is 20 volts. This is 20 volts. Now, this means that on this side, it's going to be 30 volts higher than this. So over here, it has to be 50 volts. Because 50 minus 20 will be the 30. So that's 50 volts. 50 volts. 50 volts. Notice, what's the difference? The 30. I'm good. What about over here? 50 volts, what's the difference? 30. I'm good. That's what that means. So I want you to know what the delta V means. It doesn't mean that it's got to be 0 here and 30 on the other side. It just means that they differ by 30 volts. One of the two plates, one of the two conductors, is at a higher potential relative to the other one by 30, by, whatever the value is. Yes? Now, what about this equation here? Let me say something about this one. When you look at this circuit over here, right? This one, this is, you see, this is the higher potential, this is the lower potential. So this is the plus, 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 plus. And that one is minus, 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 right? Now, when you say that the charge in this capacitor is 120 microcoulombs, what does that mean? It means that on this plate, the charge is plus 120 microcoulombs, and on this plate, the charge is minus. That looks weird. So that's minus 120 microcoulombs. Now, notice that what you have over here is this wire, right? Connecting this plate to this plate, right? That plate has positive charges as well as negative charges, except that it has more negative charges than positive charges. The difference is 120 microcoulombs. More electrons on this plate than protons. By, the charge of all those extra electrons is 120 microcoulombs. But where did those electrons come from? This wire was neutral. They must have come from this plate. So if you added electrons over here to this plate, they went this way, and the sum of all the charges of all those extra electrons over here is minus 120 coulombs. That means that that charge came from this one. So now this plate lost those electrons. So the charge on it is going to be positive because it's going to have an abundance of protons compared to electrons. So now the charge on this other one has to be plus 120 microcoulombs. And this one will be, well, minus 120 microcoulombs. So can you see that this charge therefore has to be the same as that? Because the electrons that arrive on this plate came from the other one that's next to it. Now, if you take another wire and you connect it over here and you go like that, then this electron's coming in this way. Some of them can go that way while the rest will go this way. And then you're not going to have the same charge. Therefore, they're not in series anymore. It would have to be like when you shake hands with someone with no one else touching your hands. So whatever is lost by this one is going to go to the other one. That's why you have this. Okay? So, there are some more problems, you practice, they're in series, they're in parallel, what's the voltage across them, blah, 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 so on, right? It's, in the quizzes, I don't give you formulas, but in the exams, I do. So I will give you these formulas in an exam. I'll give you the master equation, and I'll give you those, so you don't have to memorize them. But you should know how to use them to solve a problem, right? And the first thing that you need to remember is that if capacitors are connected in series, they all have the same charge. But if they are connected in parallel, they all have the same voltage. Okay? Questions?
So on the exam, how much room are we going to get for all this? Just a single page?
And the back of it. But usually you can, I'll give you a circuit such that you can solve it in one page, or if that works, you use the back of it as well. But notice, if you screw up somewhere along the way, and all the answers are going to be wrong by the time you get there. So that's why it's good to check as you do the problem. Check. Then by the time, because I might have made a mistake in the beginning, and if I never checked, by the time I got there and I checked, it would have been bad. And then, oh my goodness, where's my mistake? Any, yes?
Kind of a dumb question, but you see how like we said that B had the lower, like we're going from like, you know, 20 volts over there to 80 volts on A. So if, let's say it was the opposite way around, we would just go in the opposite direction, right? Based on the voltage, like we do everything the same.
Yeah, then in that case, this plates would be positive and this plates on the left would be negative.
Right.
Positive, negative, positive, negative,
Okay.
positive, negative, yeah, that's,
Okay.
yeah. Yes. So this is how you solve these problems. I mean, you practice with some homework and play. Any other questions? And I will choose a problem such that you won't need a calculator. I mean, I'll try my best to choose a problem where you don't need a calculator. Okay, when a capacitor is charged like that, you say that energy has been stored in it. So how much energy has been stored in a capacitor that's charged? So there are formulas for that, and there are calculations to be made. And these are formulas that I also give you in a formula sheet. So here's the calculation. See, I kind of don't like this writing. Many authors of textbooks call the potential difference between 2 points V. I rather use the delta because it reminds me that it's a difference. Because there is a potential at one point and there is a potential at another point, right? So if I want the difference between them, then it's this potential minus the other one. And so that would be delta V. But many authors of textbooks, they don't like to use the delta, so they use V to represent the potential difference. And they also use V to represent potential. So it's like using X to mean delta X. Delta X is the difference in the two positions, right? And X is the position. Delta X is the difference in the two positions. So V is potential, like X, the position, right? Potential, I guess. But then delta V is the difference of those two potentials. So I prefer that. So in this calculation over here, this V is, I should really call it dV. Okay? So the idea is this. You have a capacitor, right? And suppose that at some instant of time, this is positively charged, at some instant, at that instant, this is plus Q, and the charge on this one is, well, the negative of that. And the capacitance is this, right? Now, the potential difference between these two plates, what will be the potential difference? We call it delta V, right? Like that. And the potential difference will be what? What does the master equation say? Q over C. Exactly, right? It's Q over C. But imagine that, charges are moving. Suppose you have a plus Q charge over here. I'll just think of it as a positive charge. Oh, what the heck? Well, suppose that it's like I think of positive charges moving to the right. It's equivalent to negative charges, electrons moving to the left. Now, suppose that I'm charging this capacitor, and at some instant, I have the next bit of charge coming in, dq, coming in, right? Now, because when that charge arrives over here, that's going to change the charge in the plates. Capacitance is fixed by the geometry. So this is fixed by the geometry. But this potential difference will be changing as this capacitor charges. So I rather call this delta V, like a lowercase, but then that's for speed, right? So that's not good. What should we call it? So maybe I'll just say speed over here. The idea is that it's moving to the right. So I'll call this delta V, the potential difference at that instant of time. Right? Now, how much work, what is the energy? How much work? What was the formula that we learned for potential energy in chapter 23? Potential energy is what?
Q times voltage.
Q times V, right? So we use potential energy is Q times V, right? So delta U is like Q delta V, right? And energy, changing energy is related to work. So the work done in adding the next little bit of charge is, I can write this as dW. That equals the next little bit of charge that I add when the potential difference is this, which is delta, and it's really better to write it as delta V like that. Now, this is not changing speed, this is potential. Then if I take this expression and I plug it in here, then this becomes dq times q over c. So this is the amount of work done in adding a charge dq to the positive plate of the capacitor at the instant when the potential difference between those two plates is delta V. And when there's already a charge q in there. So this is the charge that I'm adding when there is already a charge over there. And if I want to know what is, at the end, maybe at the end, there's no more flow of charge. And this is going to have a capital Q and minus Q over here. And the potential difference is going to be now delta capital V. Right? So if I want to find out what the total work is that I have to do to charge this capacitor, then I have to add up all of these works. So this is integrating Q over C dq. The sum of all the infinitesimal works is just the total work, total energy, and then C is a constant that depends on the geometry, right? And this is Q dq. And now, if I start with the capacitor initially uncharged, and I end up with a capacitor fully charged, which I'm now going to use a capital Q, or maybe QF, oh, just capital Q, then what you get is Q squared over 2C, right? What is the integral of Q to Q? Q squared over 2. And if you evaluate that from 0 to capital Q, it'll be Q squared over 2C. So then you get this. This is the energy stored in the capacitor. It's the work that has to be done to, charge it. Now that I know that formula, I can combine that with the master equation and rewrite that in a certain way. So if I have that potential energy equation, if I have, the total energy, the work done, or the energy, I guess you can write it as, electrical potential energy is the change. In the beginning there wasn't anything. It's equal to 1 over 2C Q squared. That's 1. Now, what happens if I take this and I plug it into Q? So what am I going to get? 1 over 2C, and then that charge gets squared, and the charge is C delta V, right? And this is going to be C times delta V squared over 2, correct? Right? Or I can take this C here, and I may choose to put it in there, so this equation becomes Q squared over 2C, where C is Q over delta V. And the Q's will cancel, and I'm going to get 1/2 Q delta V. So in the next test, I'm going to write a formula like this. Capital U equals Q squared over 2C, which equals C over the times the voltage squared over 2, which equals 1/2 Q delta V. So this is the energy stored in the capacitor. When it's charged, it's Q, and its potential difference is delta V. I can either use this, or this. Which one do I use? Depends on what you give me. If you give me the charge in the capacitance, I'm going to use this one. If you give me the charge and the voltage, I'm going to use this one. And if you give me the voltage and the capacitance, I'm going to use that one. And they're all equivalent. Now, let me say something specific to the parallel plate capacitor. Let me say something specific to the parallel plate capacitor. So if you consider a parallel okay, so what do we have? We have the area of this, let's make it A, and the area of that is A. Suppose they're separated by a distance D, and we have vacuum in here. Okay. Suppose we have plus Q here, minus Q on that one. All right, so let's use one of these formulas. about I use this one? Or which one would you like me to use? Let me use this one. 1/2 Q delta V. So let me show you how the energy stored in this capacitor, it's electrical energy, right? Is 1/2 times Q times delta V, the potential difference, right? Now, would you agree with me that Q is the charge per unit area times the area? Right? So I'm going to take that and I'm going to plug it in here. And would you agree with me that delta V, the potential difference between these two plates, is ED, right? Electric field is going to be this way, right? For a set of parallel plates. So I'm going to plug that in here. Do you remember the magnitude of the electric field? What is this electric field? Anyone remember what the magnitude is?
Sigma divided by epsilon.
Exactly. So notice that sigma is epsilon naught E, right? So I'm going to take that and I'm going to put it in here. So that the electrical energy stored in this capacitor is 1/2 times sigma, which is epsilon naught E, times A times E D, right? So this is 1/2 epsilon naught E squared times AD, correct? Let me write this as total. That's the energy stored in the capacitor. Now, what is this quantity over here equal to? What is the area of this plate multiplied by this approaching distance? What does that represent? The volume between the two plates. So the total energy stored in this capacitor and its electrical energy is 1/2 epsilon naught E squared times, I don't want to write it as capital V because that also means electric potential. I'll just write it as volume. And what if I take that total energy and I divide by the volume? It will be the energy per unit volume. Or we can be a little fancier and call it what? And we're going to call it the energy density. If you have something per unit length, per unit area, per unit volume, you use the word density. Like that. Right? If you divide by length, area, or volume, you can call it density. If you divide by time, you call it rate. So that would be what? That's usually labeled with a lowercase u, not capital U, but lowercase u, and that will be what? 1/2 epsilon E squared. So notice, you can argue that the energy in the capacitor is stored in the electric field, set up by the charges in the conducting plates. If these plates are charged, there is an electric field. and the energy can be attributed or can be said to be stored in that electric field. From this formula, you could see that you could say that the energy is stored as charge in the plates, because from this formula, you can say, well, if there's a potential difference between the plates, then there's energy stored. But if there is a potential difference, it has to be because there's an electric field between them, and there would only be an electric field if they're charged. Plus Q and minus Q. Right? If there is no charge over here, from this expression alone, there's no energy stored in the capacitor. But if there is charge, those charges will generate this electric field. The presence of that electric field means that there's a potential difference between these plates. Right? And you can attribute the energy stored in the capacitor either in the charge that accumulates in the plus and minus terminals of the, the plus Q and minus Q of the two conductors of the capacitor, or to the potential difference between them, which would only be true. There is a potential difference if there is an electric field, which would be set up by the charges on the plates, right? Or you can attribute that energy per unit volume as being stored in the electric field. Right? If you have more area in the plates and more distance between it, there's just going to be more energy stored in the capacitor, but it's stored in the electric field. So this expression is oftentimes written, maybe I wrote it in my book, not my book, in my notes, like that, like electric, in the electric field. I don't know if I wrote that down. But let me show you why this turns out to be important. Let me show you why this turns out to be important. Okay, so what do we have? We have that, and I did that right here. Oh, okay, I didn't write capital E, I wrote electric. Like electric. Okay? Now, why is this important? Because when we get to chapter, I don't remember the chapter, but chapter 30, I think it is. When we get to chapter 30, we get to talk about inductors. So, I like to think of inductors as gadgets where you can store magnetic energy. So capacitors are used to store electrical energy, inductors are used to store magnetic energy. So when we start talking about magnetism, we're going to talk about inductors in chapter 30. And the capital B here represents magnetic field. And we're going to learn about this later on. And that's the total energy stored in the inductor. And area times length is a volume. Notice that the energy per unit volume can be said to be stored in the magnetic field. So the formula that I have over here was E squared epsilon naught over 2. Right? I think that's what it was, right? I don't memorize it, but yeah, that's correct. We're going to do the same. So, we're going to talk about magnetism, and we're going to talk about inductors and inductance, like capacitance, capacitors, capacitance, and inductors, inductance. We'll talk about that. And we're going to do calculations of magnetic fields. In this special case, it was for the case of a solenoid, but in the end, the result is the same. So the energy stored in the magnetic field can be written as there's a 1/2. There's a magnetic field instead of electric field. It's a magnetic field, so it's B. And then epsilon naught, we call it the electrical permittivity. It is a measure of the, you can think of it as electrical properties of vacuum, and then there are magnetic properties of vacuum, and it's a different letter. It's mu naught, like that, like that. So you can attribute energy being stored in the electric field and energy being stored in the magnetic field. Now, Those are two separate chapters. But then, I hope we have time to get there. The last chapter, it's about electromagnetic waves. And when we talk about electromagnetic waves, we write down mathematical expressions for the electric and magnetic fields. So, Gauss's law. There's a Gauss's law for magnetism here. Electric fields in that formula, magnetic fields. These four equations are known as Maxwell's equations. And it's interesting because the four equations, this one, Maxwell had nothing to do with it. It's really Gauss's law. The message here is that the thing on the right produces the thing on the left. Electric charges give rise to electric fields. That's the main message. And we learned how to apply that in chapter 22. This is Gauss's law for magnetism. Well, the right-hand side is 0. It wasn't 0 for the case of Gauss's law for electric fields. So, how much time do we have?
Half an hour.
27 minutes.
Okay, so I'll try to be brief on this, setting up what's coming up. See, if you look at those two equations, right? On the left-hand side, they are on the same footing. This is a closed surface in 3 dimensions, right? This is the dot product of the magnetic field on the surface with an area, and the left-hand side is the same, except that you change the electric field for the magnetic field. But the right-hand side of that has something other than 0. The right-hand side of this has 0 for the magnetic field. So the message here is that electric charges give rise to magnetic fields. If the right-hand side of this equation were not equal to 0, then there would be in nature magnetic charges. Just like electric charges give rise to electric fields, then magnetic charges give rise to magnetic fields. The problem is that there are no magnetic charges in nature. And that's why you have a 0 over there. Or at least, so far, we say there are no magnetic charges in nature. Yet, there are magnetic fields. So, what then produces magnetic fields if there are no magnetic charges in nature? Right? The first equation says electric charges generate electric fields. But, gee, what are the sources of magnetic fields if there are no magnetic charges in nature? Because for a while, people thought, oh, there are magnetic fields, there are electric fields. The electric fields are produced by electric charges, the magnetic fields are produced by magnetic charges, right? And then, to this day, people have been looking for magnetic charges and no one has found any. If somebody finds something and it's reproducible and so on, that should be an instant Nobel Prize in physics. And there are people working, because. So, Faraday wrote the third equation, and Maxwell had nothing to do with those previous two equations, and he had nothing to do with the third equation, the third Maxwell equation. This was by Faraday. So if you put this quantity in there, notice that the right-hand side of this, the left-hand side of this equation has electric fields, and the right-hand side is something not necessarily equal to 0. So the message here is that, notice that you have a time derivative, right? So if there is a magnetic field that changes with time, that is associated with the presence of an electric field. So if in some region of space there is a magnetic field changing as time goes on, you can associate an electric field with that. Ultimately, those changing magnetic fields is because of electric charges. And Maxwell had nothing to do with that. And then Ampere came along, and Ampere wrote the same as that equation that was written by Faraday. On the left-hand side, equal footing for the electrical magnetic fields. And Ampere wrote this only. This was missing. And Ampere was then able to show, at least with this equation, that magnetic fields are produced by electric currents. The capital I means electric currents, which are, what is an electric current? It's electric charges in motion. So an electric charge at rest only produces an electric field. If it's positive, the electric field points away from it. If it's negative, the electric field points towards it. But if the electric charge is moving, it produces, as it moves, it produces an electric field, but it also produces a magnetic field. So it was discovered that magnetic fields are not produced by magnetic charges, but rather by moving electric charges. But there was an inconsistency, a mathematical inconsistency between this equation and the second equation over there with the 0 on the right-hand side that said there are no magnetic charges in nature. So this equation was only good, Ampere's law, without this term over there, was only good as long as the currents were constant, not changing with time. Like you have a wire with 5 amps, 5 amps, 5 amps, 5 amps, 5 amps, 5 amps, this, then this was good. But if things were changing with time, it wasn't good. It wasn't complete. And this is where Maxwell came in. So Maxwell didn't do anything to the first equation, Gauss's law. He didn't do anything to the second equation. That's like Gauss's law for magnetism. He didn't do anything to Faraday's law. And what he did is he took the fourth equation by Ampere and he made this equation consistent with the second equation, mathematically consistent, by adding this term over here. And essentially, what's missing in this is this part over here, the bottom. So Maxwell pretty much said, okay, Faraday taught us that if a magnetic field changes with time, associated with that is an electric field. And Maxwell said, I wonder if the reverse is also true. If an electric field that changes with time would be associated with a magnetic field. Right? And so he just added this term, time derivative. When you take this and you plug it in, there's time derivative of an electric field. And that should give rise to a magnetic field. And so then he played, so Maxwell contributed to half of the fourth equation. Yet they are known as Maxwell's equations. Because of this term that he added, right, and then he was able to manipulate these four equations, he played with them, and he was able to show that both the electric and the magnetic fields obey equations like this. If you include that term that he added to the fourth equation, then you play mathematically with it, you do something, and you end up with an equation like this. And right away, Maxwell probably jumped up his chair because he recognized that that's a wave equation for electric and magnetic fields. And by, this is the general wave equation that sometimes, you talk about in Physics 185. And he said, my goodness, electric and magnetic fields can be solutions to a wave, an electromagnetic wave. And because 1 over the speed square, right? It's the same, 1 over v squared is equal to this, is equal to that, it's the same. So electromagnetic waves can propagate in vacuum at a speed equal to, just set 1 over the speed of the electromagnetic wave squared equal to mu naught epsilon naught, and then he, rushed to figure out the speed of electromagnetic waves in vacuum. And to his big amazement, he probably fainted at this point. When he calculated it, it was 3 times 10 to the 8 meters per second, which is the speed of light in vacuum. So he said, what are the chances that we have an accident over here? Well, maybe the accident was him falling off the chair and fainting. But if light can travel in vacuum at 3 times 10 to the 8 meters per second, and electromagnetic waves can travel in vacuum at 3 times 10 to the 8 meters per second, therefore light must be an electromagnetic wave. Because up until then, no one knew what light was. People knew that light was a wave because there were various wave phenomena associated with the propagation of light. But people knew that if there's a wave, something is vibrating. But there was a problem because we can see the sun, and between the earth and the sun there's vacuum. So what's vibrating? If light can travel from the sun to the earth into the vacuum of space, right? And light is a wave, so what the hell is vibrating in that vacuum if there's nothing in there to vibrate? So, but then the light is received over here, and it showed phenomena of waves like diffraction, constructive interference, destructive interference, blah, blah, blah. So light was a wave, but what type of a wave is it? And what Maxwell was able to discover is that light is a wave that consists of oscillating electric and magnetic fields. So he wrote down solutions, and you can represent an electromagnetic wave by something that looks like this. So the electric field in this simple picture, the electromagnetic wave travels to the right, a light wave travels to the right, and the electric field is oscillating along the y-axis. For example, so electric field does this, so up, up, up. But as the electric field does this, it's changing with time. Associated with that is a magnetic field that's vibrating like this. And if you then do a calculation for the energy transported by this electromagnetic wave, which comes up later, you plug that in. I'm going to do this in detail in class. I'll do this math over here. Wait, did I not do it over here? You write that the energy density in the electromagnetic wave, now it's EB, this is the contribution from the electric field, and this is the contribution for the magnetic field. This one is what we worked out today, epsilon naught E squared over 2, right? Epsilon naught, this is E squared over 2, this is just the rest of the dependence. And for this one, for the magnetic energy, it's this. And then you plug in, a solution to the electromagnetic wave equation, and what you get is that, let me go back. So you don't look at the details of this. What you end up getting is that this is exactly equal to that. In other words, when light comes in, when an electromagnetic wave propagates in vacuum, right? And suppose it's, the energy delivered is 100 joules, then half of that is in the electric field, the other half is in the magnetic field. So this calculation that we did today, right, may not seem important, but later on, when you make the connection with the magnetic energy, and then you put it together to describe electromagnetic waves, you discover that when light travels, let's say from the sun to the earth, right, whatever the energy is that's coming in, 50% of that energy is, you could say it's in the electric field, and the other 50% is in the magnetic field. Because it could have been 60% the electric field and 40% the magnetic field. It could have been 90% the magnetic field and 10% in the electric field. No, it's half and half. Okay? So that's mainly the importance of that expression, besides the fact that you can attribute the energy stored in the capacitor in the electric field. Now, in the case of the electromagnetic wave, then you say, if you think of it that way, right? Because if you think of the energy stored in the capacitor as, you got plus Q here and minus Q over there, and then you try to analyze the energy in the electromagnetic wave coming from the sun, where's the plus Q and where's the minus Q? Is the minus Q in the earth and the plus Q and, so just, make the connection. You can attribute that energy as being stored in the electric field. And so that turns out to be important for the propagation of electromagnetic energy through space. So, sorry for that digression, but I wanted to show you that there's more coming up later on when we talk about magnetism, and then we want to put the two together, right? To talk about the energy delivered in an electromagnetic wave. So we're going to get to the magnetism first. So we were in that chapter, right? And there's more stuff over here, but we need to move along. I can talk about this some other day. So we're going to be doing a lab this week. And the lab that I want to do is along the lines of and actually resistance. Okay? So, in these 2 chapters, we want to talk about electric circuits with a battery, and instead of having capacitors in the circuit, we just want to have what are called resistors. And we want to calculate the current through each resistor, the voltage across each resistor, the energy dissipated by each resistor. What is the energy source in the circuit? What is the what are the dissipated elements in the circuit? So it's a couple of chapters. The first one here, a lot of it is it's important. It's fundamental. It's important, but a lot of it is basic definitions and some models of electrical conduction. And then the other chapter, this one deals with the circuits themselves, and we are going to talk about resistors connected in series. Just like we talked about today about capacitors connected in series, what happens when resistors are connected in series? And then we want to talk about also what happens when resistors are connected in parallel. Today we talked about capacitors connected in parallel, so now we want to talk about resistors connected in parallel. So I'm gonna draw a circuit, and I'm gonna ask you, how is this resistor connected to this other resistor? Oh, in series, in parallel. And if they are connected in series, what do they all have that's the same? If they are connected in parallel, what do they all have that's the same? And then we're gonna pretty much use the same approach. And the master equation over here, instead of Q equals C delta V, is Ohm's law, which I'll talk about. So, and then I'm going to teach you some tricks for solving more complicated circuits using what are known as Kirchhoff's laws. And then at some point, I want to do this problem where you have a circuit with a resistor connected in series to a capacitor. So what happens? How does the capacitor charge? And I'm going to write down the equations. We're going to solve it. And then we're going to, in the lab, we're going to build just one circuit, very simple, one resistor, one capacitor. And the voltage across the, what is it? I don't remember. The voltage across the resistor, we're going to send that to the oscilloscope screen. And we'll see what the dependence is with time. Because remember, in the oscilloscope, you've got voltage on the vertical axis and time on the horizontal axis. And we're going to manipulate that signal so that it's easily drawn, sketch, or you can take a picture of it, right? And then we're going to use what we derive from theory over here, and we're going to plug in numbers. That'll be like our theoretical predictions of what the voltage should be as a function of time. And then we're going to measure it in the lab. And let's see how far those points are that we predict, how far they are from the curve that we actually see on the oscilloscope. And just, it turns out to be a simple, once you connect it, boom, boom, and you take a picture and that's it. But I like you to verify that expression. And then after that, we're going to talk about magnetism. I think I'll stop here. Next week, well, we have class on Wednesday, right? But next week is spring break, right?
Yeah.
I think we're kind of behind, so we're gonna do something tonight in the lab. Let's see how much we can do. Maybe we'll start that lab. Let me show you. I just posted it on the website. Let me just show you. So it's number 5 on the oscilloscope and resistance. So what I want to do here is I want to show you how to use the oscilloscope to add and to subtract voltage signals. So we're going to send in a voltage signal to channel 1 and another voltage signal to channel 2. We're going to know what they are, and we're going to subtract them, and we should know what the difference should be, and we're just going to check with the oscilloscope. The reason why we want to do that is because then you have this circuit here, this one, this circuit. I mean, it has to do with resistors, and but you have this circuit over here, and suppose you have this. This is like a voltage source, and then you have a resistor connected in series with the other resistor. Suppose the potential here is 0 at some instance. Suppose the potential here is 0, and we want to measure what this potential is. Sort of like this. You have a battery. Suppose you have a battery plus, minus, and you have a capacitor, and you have a capacitor. Suppose the potential here is 0 volts. And here it's something, I don't know, 10 volts. So then we know that this is 10 volts. And we know that this is 0 volts. And what we want to do is we want to measure this potential difference. The problem is that suppose the potential here is 4 volts. Then this difference is going to be 6 volts, and this difference is going to be 4 volts, right? So the 4 and the 6 will give you the 10, not a problem. The problem is that when you make that measurement, right, and you use the oscilloscope, in the oscilloscope, you have this input to channel 1, input to channel 2, and the input to channel 1, you have a coaxial cable, and you have a wire down the axis, and you have another one coaxial with it, and that one, on the outside, the potential is 0. So, if you connect channel 1 and channel 2 to the various points over here, when you connect, if you go straight to here, right, this is not 0. Because the unit is also connected to the wall outlet. So what you need to do really is make a measurement of this potential on channel 1, and then make a measurement of this potential so they share the same ground, 0, on channel 2, and then take the difference between them. Because otherwise, if you bring the cable and you just connect over here directly, you're forcing this to be 0. And you get the wrong reading. So I just want to show you how to find a difference of 2 voltage signals, right? So at first we're just going to set it up, right? And we'll know what the answer is. And then I want you to build a little circuit like this using a breadboard. And then, what is this voltage here? Now, what should it be given these values and so on? That's still beyond the scope of what we can do. But the point is that if you measure this voltage, and suppose it's 10, and you measure this voltage, so in channel 1 this is 10, and you measure this voltage, and it happened on channel 2, let's say that's 4, then this one has to be 6. So it'll be relatively quick. But I gotta show you how to make these connections. I gotta tell you about that. So that probably takes a little while with the breadboards. Okay? There's another part to that lab, which is also supposed to be very simple. It has to do with resistors. But given that we haven't talked about resistors yet, because we're trying to show something here from theory, let's do that part next week. So instead of having one long lab where half of it you may not know what's going on, let's do one half, understand that. And then next week, by then, well, not next week, the week after that, right? By then we'll know enough to be able to do this part and get more out of it. Because if you do it without having looked at it, you may think this is hard. But if we talk about it, then you'll see that this is not so hard. Just, it'll help you understand better the topic. All right, I'll see some of you later, right?